Hi and welcome to this webinar, End-to-End Computational Fluid Dynamics on AWS. I'm Neil Ashton, I'm Principal CFD Specialist Solution Architect. And I've spent most of my career looking at high-fidelity CFD approaches and trying to, push increased accuracy. But it's really struck me how this can really only happen when there is a greater access to high-performance computing resources, which was the focus of a previous webinar I did a few months back. But today, in addition to talking about that, I also want to talk about, the need to look at the whole CFD process, and how we can optimize it all to really get those improvements in accuracy and efficiency. So the overview today is basically going to look at, first of all, what is our challenges for the sector, for the automotive sector. Then some discussion of typical CFD workflows and some of the challenges at each part of it. A section then on how AWS can help to solve some of those challenges, and then a short demo of just giving an idea of what it would actually look like, and then just summarizing at the end. So I suppose my background has actually quite often been around automotive and motorsport. I did spend some time in Formula One, both at the beginning of my career and more recently with Formula One management. But when I've been developing these new CFD methods or looking at testing them on large HPC resources, it's quite often been with an automotive focus. And actually, I really wanted to try and help to move the community forward. And I organised the first automotive CFD prediction workshop at the end of last year with Professor Gary Page from Loughborough, which really tried to bring everyone together to see, what are the challenges to the automotive CFD community and how can we move things forward. So I put that slide just to say that hopefully I have some appreciation of the challenges that the sector is facing. The way I like to start it is it's from the big picture, I suppose, and that's that autonomous electric connected vehicles really are the future, and this has quite significant impacts on CFD. Electric vehicles typically require an even greater focus on efficiency due to battery range. There's even more of a focus now on trying to drive the efficiency, reduce the drag, to extend the battery range as much as possible. But more so than that, if you think about autonomous connected, it means a complete rethink of the traditional shape of even cars, because you don't need necessarily to have the driver at the front and the traditional 4 or 5 passengers. There's some of these companies are coming up with really revolutionary shapes, and that means that you can't just take historical data or iterate from a previous design. Some of this conceptual work is really brand new geometries and therefore flow physics, and therefore your CFD needs to really be as accurate and fast as possible. The second challenge is around the WLTP, so the Worldwide Harmonized Light Vehicle Test Procedure, which I'm not going to go into depth, but I want to pick out one bit from it, which is simply that, in the past, an automotive company could take one of their vehicles, do the required testing to figure out the CO2, the fuel efficiencies, and then present that number on the TV adverts and the brochures. But now with the new WLTP rules coming in, that mean that every option needs to be tested, because of course the reality is that you could have a number of a certain CO2 or fuel efficiency, but that could change quite a bit if you were to add the big tires, sports tires. You add a roof rack on the top, change some of the spoilers. So now companies have to test all the options and provide them as CO2 or fuel efficiency additions. This is putting real pressure on wind tunnels, to be able to get through this and and also the coast down tests. So many are, turning to CFD to say, well, can this actually be used as a certification method? And the obvious questions then come is, well, is it accurate enough, repeatable enough, and actually can the timing be good enough that it's as fast or faster than physically making something and taking it to a wind tunnel or doing a coast down test? So all of these pushes the need for a highly automated, highly efficient and accurate CFD process. Now, the next slide, anyone who knows me, I probably show this actually too often, but really there is a move to increase in accuracy, to move beyond these kind of low fidelity RAN CFD approaches, and to move to these kind of higher fidelity transient ones that have consistently shown increased accuracy. This graph kind of shows you an example of lift prediction for various car shapes, and showing that on the right hand side of the graph, moving to these high fidelity methods brings you much more in line with the experimental than these low fidelity ones. But of course they take anywhere between 5 and 20 times more expensive computationally. And that's why in previous webinars I've focused on how AWS and HPC can help this. I should say as well that one of the big things that I've been trying to do, and I mentioned, is about bringing the community together. And this was why we organised this first automotive CFD prediction workshop, which I think was really successful in bringing people together and seeing these challenges around, high fidelity CFD, the importance of HPC, flexibility, and we're really pleased that there's going to be a second workshop next year. We're just about to launch the website for that. So if you want more details, reach out to myself or Charles Mockett from AppStream CFD, who is actually the lead for the second workshop. So I think that would be interesting to really move the community forward. But focusing today on the CFD workflow. I mean, the precise workflow is dependent on the software packages and the company setup. But the general components are shown below, and the efficiency and accuracy is more than just the solve part. It really is right from the beginning, from the CAD all the way up to generating the post-processing. And I want to just take a few moments to dive into each of those components. So if we start off in the the CAD part, what is this? Well, it's typically a team of engineers to draw these parts. If it's a startup, it could just be one individual. If it's a big automotive OEM, it could be a whole team of surfacers who are doing this on a daily basis. The challenge, of course, is that there are many different areas that need this surfacing, from the A and B surfaces, even to the tires and to the engines. It all has to be drawn, and it's often done in varying formats in different parts of the organization. And if we look from a resource point of view, it's hours to days or even weeks to draw an automotive model. But typically it's Windows based. Most people like to use things like Siemens NX. You need a GPU, you need moderate RAM. And of course, the thing that most CFD practitioners know very well is all CFD codes need some form of a cleanup of the CAD to enable a surface that can then have a mesh generated on. You also typically need to do some definition of the boundaries, whether it's simple reporting of forces or defining where porous media are, or MRFs or fans. And the challenge here is simply that the input can be many CAD formats from many parts from different organizations, subcontractors, and can be extremely complex to adjust. And it's typically a very manual process. Nowadays, software like Answer by BetaCA Systems, tries to do some of this automatically and greatly improve the speed that you can do it, but it's still quite an intensive process. And this is days to even weeks to clean up a model. Again, it's typically a Windows thing, although some people do also run this on Linux machines. Typically with a GPU. And moderate/high RAM, for the most complex models when you have many parts inside of it. Of course, the next bit is the meshing. Here there are many options, but for the automotive, it is typically unstructured for finite volume type approaches, and then maybe some sort of Cartesian mesh for lattice Boltzmann with some immersed boundary or cut cell approach. The real challenge here is it's rarely a one-time exercise, but many iterations are required to reach a suitable template, and quality. And then once you have that kind of templated thing, then you could be running a batch mode and fully automated. But it's definitely an interactive manual process at the beginning. And of course, the real challenge is that it needs to be often run. So there's a dependency on the solve in a kind of a loop. The resources is, hours to days to mesh, depending on the size of the case and the complexity. Is typically Linux, although maybe for smaller things and for personal preference, it could be Windows. It's the CPU that's driving this, but, a GPU to maybe visualize these large grids. Large RAM, you could easily get beyond 64, 128, more than 200 or 300 gigabytes of RAM. Starts to put a pressure on really the sort of, desktop that you might do this on. This is why some software runs on, shared memory, single node, or there's others like SnappyXMesh with OpenFOAM or, StarCCM's internal meshes that can actually run across multiple nodes. Of course, the kind of key one is the solve. Ultimately, you're going to solve some equations over the grids that you've generated. Broadly split among the finite volume codes, StarCCMs, your Fluents, your OpenFOAMs, and then the lattice Boltzmann codes that are quite popular in the automotive space, like PowerFlow. Many others here, of course. The challenge is really accuracy and computational cost, and the fact that they are very clearly linked. So you really can't get one without the other. But there is a clear trend towards high-fidelity methods, these kind of DES transient ones, just because of the clear improvement that they give. In terms of resources, it's probably low hours for maybe the RANs, pushing up towards maybe days for the hybrid RANs. Of course, this is very much a function of the number of cores that you can run. Typically hundreds, maybe going up to thousands ideally. This is where the difference between the CAD and the mesh start to come in, because now you really do need some sort of Linux supercomputer, large amounts of RAM, some sort of low latency, high bandwidth network interconnect, and high memory bandwidth on the nodes themselves. But of course, the final one, and arguably the one that really makes the decisions, is what data you can extract and information you can get from those simulations. What can you get out to understand the flow physics and to make some design decisions on what you're going to go forward with. So the challenge really here is a data challenge. You can be running hundreds of simulations, but you really need to find an efficient way to get the data out of them. It's typically a mixture of batch processes linked to somehow the end of the solution, but often also interactive. And the key here is you may want to revisit the data many months after it was produced. The resources here are, dependent on the size of the solution and the grid, but, typically very high RAM, a GPU to do the kind of rendering, and some, good data storage. The challenge here is typically the fact that you want to potentially look at it interactively, maybe on a Windows machine, but you want to generate it in batch, potentially in parallel on Linux machines. So really the challenge is that the whole workflow is only as fast as the slowest part, really. And traditionally, the focus has been on how can I make the solve faster? And that's obviously one of the things I covered in the previous webinar and we'll talk about later. But really, I want to say that how can we, solve all the parts? How can we solve the cleanup bit and the meshing bit that maybe is on a Windows machine? There's such different resource requirements, but they all have to have a data that can, be available in a fast, secure, and durable way. And this is where I'd like to think that AWS can come in and really make a tangible difference to improve the whole workflow efficiency and ultimate accuracy at the end. And, the reality is that, the world is changing, data centers are changing, and millions of customers are actually moving to AWS. Startups, big enterprises, and even public sector, universities. And they're typically doing that for 5 core reasons. And the first is agility and elasticity. So if you think about it, for most companies, it takes weeks or even months to provision and purchase and set up servers. If you want to go and get a new 200 gig, fast workstation, it could take weeks or a month for you to actually get it. And all during that time, you're having to do your CFD work on suboptimum hardware. Or maybe you have to make changes to what you want to do. You don't run as accurate or as big simulation because you don't have the hardware. And that's a real shame because that's limiting the accuracy and the ultimate potential of CFD. Whereas on the cloud, you can get those resources in minutes. If one day, most days, you just need a 30 gig, pretty standard machine, you can get that. But if just, for that afternoon, you have a case that comes in and you need to suddenly do something big and you need 200 gigs of RAM, you can just scale up and pick an instance that has 256 gig of RAM, for example, use it for a few hours and then spin it back down. You didn't have to wait a month to get it. You just spend a couple of minutes and it's up. It really is that kind of agility and elasticity that is extremely attractive. The other one is the cost optimization. So the fact that you don't have to, lay out this capital to go and buy these things, but instead you can just pay as you go, gives a lot more flexibility, and particularly for startups, who really don't have the legacy infrastructure and just want to be really agile and really control their costs. But this is also true for the largest enterprise that are looking to save money and saying, well, really, we only should have the hardware needed at the right time for the right use and not just buy something that somehow is in the middle. The third one is the kind of global scale. You always want to minimize delays and interruptions, and you want to support any country. Many of the large automotive companies are not just in one country, that they're based all around the world. And really you want to be able to give the same, sort of hardware infrastructure and performance no matter where you are. And the fact that AWS, spans 77 availability zones at the time of this recording, 24 regions, you really can touch really everywhere in the world and have the same resources and the same performance no matter where your company resides. The fourth one is security, because at AWS it really is the highest priority. The same security isolations are employed that would be found in any traditional data center. These include, separation of the network, isolation of hardware, isolation of storage. And the great thing is that, as an AWS customer, you inherit all the best practices of AWS policies, architecture, that is built to satisfy the most security sensitive customers. And finally, it's reliability. The fact that it is proven. AWS, it's one of the main reasons that AWS grew as it has, because we've spent over a decade building one of the most reliable, scalable, and cost-efficient infrastructures. And as I mentioned, the fact that we have this global scale gives you the kind of safety net that that all the data center are designed to be able to withstand excessive bandwidth connections or disruptions, so that you always are able to connect to your data and carry on with your work. So if we actually go to what practically, though, can be done, and I wanted to break this down, I suppose, into some of the core services and the bits that I'll later show in the kind of the demo. So if you focus on the CAD and the CAD cleanup and the post-pro, many of these are Windows based, and really you just want to be able to have the right resource at the right time, and essentially just stream that application. And we have a service, Amazon AppStream, that is a fully managed service to basically just stream Windows applications as you need them on the hardware that you want, and AWS is managing the infrastructure for you. The second key bit of this is you want to have some consistent storage that is available across all of them. And we have something like Storage Gateway, where you can actually store things, for example, in S3, our object storage system. And then each of these applications can see that same storage. And with something like Storage Gateway, you can even express that as a volume on your on-premise system. So you can be sat on your own machine, see the same files, switch over to AWS, and those same files are there ready for you. And I'll show that later off in the demo. But the really cool thing about AppStream is that it's a managed service, it's secure, it scales up and down, and it's just pay-as-you-go pricing. So you can have a really nice thing where you can just create this Windows-based machine. You can install some applications, and then your end users just see that application. They don't have to worry about anything else. And there's a range of different instances that you can use. So, for example, you may say, well, I only need actually, 8 gig of RAM for some basic machine. So you could provision that, starts 10 cents per hour. But if you go all the way to the other side, with some of the Nvidia T4s, so the G4DN, that goes all the way up to 256 gigs of RAM and 64 vCPUs. And that starts maybe around $1 an hour. Now, you can, switch whatever you need. So one day you can be using the standard one. For a few hours, you can use the G4DN. And that's really nice that you can kind of be super flexible. The other cool thing is that for AppStream, it actually streams from many locations, all around the world. And there's a very, practical example of this that, I'm a visiting fellow at Oxford University. And as part of this, I still help to teach a class every so often. And I was actually doing something earlier this year where, because of COVID, the class would normally have been done in in a computer lab. Everyone's there on the desktops that they have. They install the CFD software and we do it, no problem. But because of COVID, the students were actually all around the world. And I decided that I would take advantage of AppStream because I wanted, rather than them just doing a remote desktop into some machine that's in Oxford, which would give really poor latency for someone who's on the other side of the world, I decided instead to use AppStream. I created a single image. I installed the software, I think it was StarCCM at the time, and I cloned that image and I copied it to Singapore because we had a couple of students who were in Singapore. And then I copied the same image to the east coast of the US because it was something in the US. And with literally a couple of clicks of the button, they were able to access that resource with a really low latency because it's really close to where they were. But for me, it was just simply a matter of creating it once and copying it. And for them, they had exactly the same experience as everyone else. So this was an academic example, but you could equally pass this to an enterprise automotive company who wants to be able to have the same sort of provisioning of software and resources all around the world. I suppose the cool thing is that, traditionally, if you were trying to do this on premise and have some, virtual desktop infrastructure, you would have to look after all of this, right from the bottom, from the power and the rack and the stack, up to the management of the instance. Whereas on AWS, suddenly now this moves to AWS is able to take all the lower half with the AppStream managing all the physical security in the data centers, the hypervisor install, the control planes. And the only thing that you need to do is essentially just manage the image and any, like Active Directory kind of services. So it really does let you focus on just making your customers get the resources they need and not having to focus on the kind of infrastructure side. And the other cool thing is that it's actually very secure because none of the data resides on your local device. So, if you have someone who can just be accessing it from a laptop or anything, you don't have to worry about where that data's going. The apps are all centrally managed, and you can easily scale it up, on any resource that you want. The back end of this, which is doing the streaming, is a thing called Nice DCV. That is actually something also available to visualize, head node or resources on a cluster or on EC2 instances. And this is using HTTPS, secure access, encrypted pixel stream, and actually gives really genuinely good latency and quality that you'll be extremely impressed by how it feels. In terms of pricing, there's two models. There's essentially an always on and an on demand. The always on means the instance is always running, it's ready, and you can instantly connect to it. Of course, you pay for it while it's running. With the on-demand is that after a certain amount of time, which you can configure, the instance is stopped, but it's ready to restart in only 1 to 2 minutes. And then you basically just pay while you're using it. So you kind of have two options depending on your cost needs. So that was the kind of the CAD side. And again, I'll show you this a bit later in a practical demo. But for the meshing and the solve and the kind of batch post-pro, we go now towards the more traditional Linux supercomputer. And we have a thing, AWS Parallel Cluster, that makes it super easy to provision and create a cluster, in a matter of minutes. Underpinning all this is, a really good file system like Amazon FX for Lustre, high-performant parallel I/O. It's, the sort of trusted file system based on Lustre that is in many of the top supercomputers around the world. And of course, again, something to make sure that you can see the data between your Windows and even your on-premise is something like Storage Gateway, which, again, I'll show a little bit later on. And the reason that, the HPC is a core part of this, and the real reason that AWS gives some genuine value is, because of this, is that many companies are having to essentially fit their workload around their hardware and not their hardware around their workload. You typically have something on the left where you have finite capacity with long queues and some sort of Tetris game of trying to fit your resources in. On AWS, you can get away from that model, and instead you just focus on a per job, what needs to be run in the most performant way or the best price, or you can combine the two. We have massive capacity, so you can speed up your time to results, because instead of running, let's say, on 100 cores, if you know it can scale well to 500 cores, run on 500 cores. There's no need to be limited by that. And that really does change things, because it starts to make a real focus on time to results, and it can genuinely speed up your turnaround time. And of course, the reason why people want to do CFD in AWS is because of this large-scale infrastructure. They have the latest technology, so as soon as there's new chips coming out, whether it's CPUs or GPUs, whether it's x86 or ARM, and of course the fact that you can be flexible and you can just spin them up, try them, spin them down, and ultimately reach a point that you're happy with. Now this global infrastructure is something that really does underpin it. The 24 regions, 77 availability zones at the time of this recording means you can really easily share resources around the world and make sure that wherever your company is based, you can get access to what you need. And transferring data across the globe is made simple and secure. And we really do have the broadest and the deepest platform choice. I mean, if you go down the instance list when you log on to the AWS website, there are so many instances to meet your needs. Whether it's the speed of the CPU, whether it's the memory, whether it's the storage attached to it, whether it's some sort of many core device like a GPU, the networking, on the storage side, it's just, there are literally everything that you could want, and you can just go in there and build it to how you want for your workflow. And of course, the kind of key components are things like C5N, which is our Intel Skylake, 100 gigabits network bandwidth. This is the kind of go-to for CFD. If you need higher RAM, then you can go for the M5N, or even higher for the R5N. And this is backed by EFA, Elastic Fabric Adapter, that gives you that really good network performance. On the GPU side, you've got the Nvidia V100s, latest generation. That for CFD codes that can actually run on GPUs, and I've got an example of one a little bit later. Of course, we have the ARM C6G that delivers really good price performance, over x86 for many of the CFD codes like OpenFOAM, and it just gives you the choice. It's up to you whether you want to run on a Intel, AMD, ARM, or GPU. You really have the choice. And of course, underpinning these, which are really needed to scale these tightly coupled applications, is EFA, the Elastic Fabric Adapter, and this really does have the high network bandwidth, low latency that gives you that good scaling, so you can take advantage to reduce your turnaround times. And finally, FX for Lustre is that thing that underpins. You need a really good file system. You need something that can give you that performance, so you can scale up to be running, thousands of cores and many jobs all at once, and not be limited by your file system. So, it's useful to show a few graphs just to show some ideas of scalability. We've tested many codes. We have an internal benchmarking team, which is just done to try and give you the best performance possible from these applications, so that when you run on AWS, we can say these are the best settings, these are the best MPIs, compilers, so you can get really good performance. And if you pick something like OpenFOAM, you can see good scalability, to thousands of cores. This is an example of the simple motorbike case, scaling beyond 2,000 cores. And of course, at some point, it's down really to the linear solvers in the codes rather than the actual hardware itself. But you can see it gives good performance. For something like StarCCM, I showed in a previous webinar, you can run out here to 7,000 cores, a good scaling, beyond 100,000 cells per core. And the same for Fluent, and this even had an example against an on-premise Cray machine. But we've run pretty much every CAE CFD code in AWS, and we consistently see excellent performance and scaling. I think one of the interesting ones is actually the ARM. I mean, this is a blog that I did recently comparing the performance of the C6G versus C5 and C5N. And whilst naturally the scaling won't be as good because the C6G doesn't have EFA and has a lower network bandwidth, what's really interesting is the price performance is substantially less than the C5N and the C5. So it's nice for the customers who really care about price performance, which in my experience is actually most customers. Then I'd highly recommend to look at the ARM, and for things like OpenFOAM, it's super simple to compile and use. But one of the actually interesting things that we've been working on recently with one of the AWS partners, Zenotech, is around GPUs. And you see here really good speed up from going on GPUs. This is an example of a code that can support both CPUs and GPUs. And if you look at the P3DN using the Nvidia V100s, the iterations per minute is faster than any of the CPU options. And if you scale out the CPUs, you would never reach the speed of the GPUs. Now, you may be questioning and thinking, well, okay, probably the GPUs are more expensive. But actually, you'd be wrong. The GPUs actually end up being cheaper because they deliver such a good performance for the instance. So these P3DNs, in the 24 have 8 V100s per instance. And so when you sum up the costs, and of course the costs are all available on the website, you actually see that you can see not only faster time, but cheaper on the GPUs. So this is really exciting, and I hope other people in the CFD community will take this as a nudge to keep focusing on GPUs, because I think they really can offer a good price performance benefit. Now, one of our, customer case stories is Formula One, which is a good example of, somebody wants to be running CFD and really to kind of accelerate their whole process. And thanks to AWS, we've been working closely to move from, around 200 cores maybe to more than 1,000, and to try and push that workflow and solve from 60 to 10 hours. And it's something we're still working on on a daily basis with them to try and optimize and help them further. Another really good example is Ineos, the America's Cup sailing team. And we also work closely with them that they needed to turn around a huge database of runs, 15,000 designed in less than a month, and this really was around 20 times more than they could on premise. And this was because they were able to take advantage of the global capacity, and we built a custom solution with them, and even used Spot to really lower the cost for them. And this was a really good thing, and I hope it has a lot of parallels with companies out there. Okay, so the demo today is the DriveAir model, which is a popular open source model. This is actually going to be running OpenFOAM v2006. It could be any other flavor of OpenFOAM. I actually used an answer generated mesh, so thanks very much to B2CAE for the license and for the mesh. And this is actually part of work that we were doing with them for the first automotive safety prediction workshop. So these meshes are actually available on that website. So if you Google that workshop, you can go in and you can download all the meshes and run them yourself. End up being around 111 million cells. This was actually a DDS simulation, although I won't actually focus too much on the kind of stuff behind it, but really focus more on the workload and how you could use your individual process within that. I'd also like to thank Siemens for the Siemens NX license, because we're actually going to show how you can use CAD as well as part of this whole workflow. Okay, so let's start the demo. So what you see in front of you is the DriveAir model, and you can see it's been opened up in Siemens NX. And these are the files that have been downloaded from the TUM website that offer the open source model, and I've just loaded them in NX like I would do on any normal machine. The difference here is this is a Windows version of NX that has been streamed via AppStream, and you can see I can move the model around, I can add or remove parts. Obviously this is a simplified CAD model compared to what you would typically get for an automotive OEM, but you can see it's exactly the same. Except the difference is that this is actually one of the only applications that is on here. I don't have a full Windows desktop, I simply have the application. And in fact, I can see the catalog of applications that I've decided to stream. It's NX, it's actually something to connect to the license, and it's a work directory. If I go into the work directory, I can see a normal Windows, Windows Explorer, except in addition, I've got a shared network drive that we're going to use to share between our Windows and Linux. And in theory, I could also have this on my home computer as well. Now, I've actually gone off and saved this CAD file here in a part file and STL file. And the point is that I can actually now access that from another AppStream image that is more optimized for the next stage. So this is a relatively small graphics design AppStream image. It's just got a few cores, maybe 15 gig of RAM, which is probably enough for the CAD that I need to do. But the next stage is I want to actually go and do some cleanup and look at the meshing. So I would go to another AppStream image. But maybe let's decide and show you how that actually works. So let's go to my management console and let's go to AppStream. Now you can see in AppStream, you've got stacks, fleets, images. And the key point here is that you can create an image that you can then go off and install all the applications you want. And then you can provision a fleet with a certain instance type. So I've got a 16x large, so that's 256 gigabytes of RAM, Nvidia T4 driven GPU. And I can actually get that fleet then to be dynamically scaling to however many users I decide to create. Now it's just me, so I'm only going to have one spinning up, but if the more users I add, then it will automatically scale up to deliver more of these instances. And then I can create a stack that has certain software and images aligned to it. So how do I actually build the image in the first place? Well, if I go to that, you can see it's just like a normal Windows machine. And we have an image assistant here that helps you to build and install the applications. So I've gone and installed Answer. I would use my image assistant to actually help me to create the apps that I want. So Answer, PowerView, Windows Explorer. I can configure them, optimize them, and then save that image, which will then appear in these images, which I can then assign to a fleet. Now, what that in practice means is that when the end user logs in via their email and password, which could be also an Active Directory linked username, they'll come up to something like this. So if I look at the catalog, all you see is the 3 applications you want to stream in the settings that you've set up in the image, and you can start going. Except now, whereas before I was on a small machine, I'm now opening up something which has 250 gigs of RAM, and it provisions in only a few minutes. So let's open up this file. I'll go to the same shared system. Remember, this is a different instance, different AppStream, but it's got the same file system attached to it. So now I can open up something that actually has this driver in Answer. It's already been cleaned up, but you can appreciate that you could be cleaning this up. And here we go. So the model's here, so I can zoom in. I can look around. You can see the actual solutions being attached to help them to generate the grid. I can actually go in now and look at the model a little bit more closely, turn on everything. And now I can actually zoom in and I can do everything I want to do to clean up this if this was a mirror that I had to attach. Now, what I've got here is that I could actually mesh here. I could use this Windows machine and I could actually generate the mesh. It's already been set up in a batch process. So I could actually play around with this now and run it and generate everything that I want to do in a Windows environment. And this may be great for that kind of interactive point where you're building up how you want to generate the mesh, and you want it in an interactive, potentially Windows-like environment that I can just switch between my 2 windows. I've got my CAD box here, and I've got my Answer box here. As I said, one's got 10 times less RAM than the other one. It's also much cheaper. This is the more expensive one, but I'm only going to use it and pay for while I'm using it. So I could kick this off, but what I'm going to do instead is actually now move to a Linux environment, because I want to run this in a batch mode to generate this grid, and then I want to actually run this in OpenFOAM. So let's now move over to the cluster. Okay, so we're now on to the Linux cluster. And a previous webinar I did, the Motorsports CFD one, that went into more detail of actually how to create a cluster. So I definitely recommend you to have a look at that one. If you just Google AWS Motorsports CFD, that was, really showing you how to go and type the commands and make the configuration script. In the interest of time, I'm not going to go through that again. But what I have done is made a similar cluster, and I've used the DCV app that's available on most operating systems to connect to the head node. So I have essentially a GUI to be able to interact with the cluster. And if I do ls, I can see that there's OpenFOAM and Answer installed here that I did previously. What I've got is also then a couple of file systems. Parallel Cluster makes this very easy to spin up this whole cluster and then specify what file systems you want. So I actually have an Amazon FSx for Lustre file system that I created actually outside of Parallel Cluster, linked to an S3 bucket. It's a 9.6 terabyte system based upon SSDs, really good throughput. And then I just simply specify in my config that I want to mount that particular drive to the cluster. And then I can see all the files, or I could mount it to multiple clusters if I wanted to. The other thing that is probably relevant for this as well is the /gateway. And the /gateway is essentially exactly the same drive that was on the Windows machines, on the AppStream. And I wanted to show this one because it does enable you to share files between different operating systems, between different services on AWS. But probably also most relevant is that this could be mounted on premise. The whole point of Storage Gateway is it enables a hybrid cloud sort of architecture, so you can easily have the same file system, which is really nice and has a really good user friendliness. So I've got the files there. So if I go back to my FSx, you can see I've got multiple folders here. And now one of the cool things is that I'm actually using a version of Parallel Cluster that will be released very shortly that has a feature that has been quite sought after, which is the multiple queues, multiple instances. And so what this has enabled me to do is the cluster essentially was based upon a very simple configuration file where I specified multiple queues. So I've got a debug, a mesh, a post, a solve. I specified what instance I want for each of those queues. I set some arbitrary number of nodes that would be the maximum. It could be really anything. And in addition, I set my file systems and things like that. So I set up a debug queue because I wanted something I could easily just submit little jobs to. I've got a mesh queue because meshing often requires different instances than solving. So I've got an M5 24x large, so it's got 384 gigs of RAM. It's a Cascade Lake 48 physical core machine. Really good for meshing even just on a single node, and particularly on multiple nodes if you need more RAM. For the post, I've got a GPU, the Nvidia T4 based ones that is actually what's on the AppStream image as well, 256 gigs of RAM. And then for the solve, I've got the C5N 18x large, and I've got it in two configurations. I've got an on-demand queue and a spot queue. And so I can easily just use, in this case, slurm partition command to submit jobs to any of these queues. And you could imagine that this could be really done for also different CFD codes, for CAE codes, if you've got structural codes that require different sort of hardware. And this is fantastic because you're not limited to a single hardware type. You can be flexible. You can pick the instance that what you need for your code today. And tomorrow, if you need something else, you can just change and spin up some different type of cluster with a different queue just to match your needs. And it's a really, really nice feature. So for the meshing, I'm actually going to use the mesh queue, the M5N 24x large, and I'm going to submit the job now. So if I go to mesh test, so I've got essentially the same answer file now, just with a Python script to be able to run this in batch mode. And I can just submit this to the cluster. SQ. So essentially now what it's doing is it's going to spin up those that instance to provision it. And previously I was only paying for the head node, which was a relatively small couple of core machine that was costing me only a few dollars a day. But now when I actually ask for a resource, now it actually goes off and spins, and ultimately I'll start paying for it. After a few minutes once it comes up. And then once it finishes, there'll be a few minutes where it'll stay up to see if there's anything else it needs to do, or it'll spin down. And then I'm only paying for while I've used it. That's a really nice kind of, again, elastic feature that is similar to AppStream in the sense that you can just use it while you need it, pay while you're using it, and then you can just spin it down. So this is going to go off, provision it, and it's going to start to create this batch case. So what the next stage is obviously this is going to go off and create it, and it's going to take some time, half an hour or 40 minutes. I've already prepared this, and the next stage, in the case of using an answer mesh, is to decompose it. Now these are quite large cases, so actually to do the decomposition, you need to really have something with a decent amount of RAM, and it's a serial process essentially. So I'm going to submit this job also on the mesh queue, and this is going to go off and actually do the decomposition of the case. And I'm actually going to do the decomposition to 1,400 cores. The reason for 1,400 is, it could really be any, depending on your needs, but the mesh is around 111 million cells. So, OpenFOAM typically for these sort of industrial cases doesn't scale that much beyond 100,000 cells per core. So around 1,000 to 1,500 cores is probably the right number. So I've already got a case that has been decomposed. So if I go to my solve test and go into here, so that's already been decomposed to the 1,440 cores, and now I can actually just submit this to the cluster, except now I'm submitting it onto the solve queue, the on-demand solve queue, on 40 nodes. So this is again the ability to have these multiple queues, multiple instance types, and you could very easily script this such that you can daisy chain the jobs together and have it that let's say in the case of SnappyX Mesh, it could be meshing, and then as soon as it's finishing meshing on the mesh queue, then it's going to go into the redistribution. It's then going to go into the solve queue, and then could go to the post queue. So what I've done is I've set this off to run. These are all going to spin up, and we'll have a look at it once it starts running. Okay, so you can see now I've had a look, and it only took a minute, just over a minute for those nodes to come up, and those jobs have all gone off and started to run now. So if we look at the mesh test, you can see it starting to go through the case and starting to actually generate the mesh, and you can see the same thing for the others too. So if I just go back to the queue, so I could submit multiple things now, and I could really customize this depending on how elaborate your CFD process is. So what I did before is I already actually ran some of the case through, and I actually have a post-processing folder that has some slices and forces, etc. So what I'll do is I want to be able to just interactively look at this, and in this case I'm going to use the example to put it onto the storage gateway and look at it on the Windows instance. So what I can do is just, again, arbitrarily just copy this over. And it's now going to copy those files over to the gateway. It's maybe around 1.5 GB, something like that. And then that will show up on the AppStream image in the same file system. Okay, so if we move over to the file system, so we can see now if I actually look in here, you can see post-processing is already there. Now let's open ParaView. Okay, so let's go in and open up say the car one. And so this will just take a moment for it to load in, and then we can have a look at the car post-processing. Okay, so we can see we've got some initial solution. And now look, I can just spin around this model. It's actually very responsive to be able to move around. This is obviously just really a demonstration case and it's not the full solution, but hopefully you can see that I've essentially been able to, from my own laptop, which just happens to be a Mac, so I can't really install this sort of software anyway, I've been able to go through and use the CAD program, been able to play around the CAD. I can then just save it out. I've moved over to another image where I've been able to, if I wanted to mesh and clean up geometry. I've then been able to switch over to a supercomputer where I've been able to provision more than 1,000 cores in a couple of minutes. I've then gone through and been able to use multiple different hardware types at my choice, run the case, and then copy some post-processing and jump to another Windows machine and look at this in PowerView, all in my fingertips, and being able to provision this in a matter of minutes. I genuinely think that this is quite a big thing for the CFD community, to be able to have that sort of power in your hands, that I could easily scale this up and be running, a 1 billion cell case now, because I can just have a large instance for my meshing. I can have a large instance or set of instances for the solve and the post. But equally, I could be running a 500,000 cell case and just pick the instances to be much smaller. So I hope this demo is, obviously being on relatively simple terms in terms of the geometry and the complexity of the workflow, but I hope you can appreciate how you could use this to really do something quite innovative and really speed up the whole CFD workflow and not leave any bit of it to be the bottleneck. Okay, so that was the demo. So how about cost? Well, there's 3 main cost models in AWS: spot, on-demand, and reserved instances. And we publish all these prices per region for all the services on our website. So please do go and have a look. So starting on demand, that's our standard price model. That's probably what most people will be using on a daily basis when they start on AWS. Reserved instances are for those known or steady workloads where you can get pretty substantial discounts by paying partially or completely upfront over 1 to 3 years, for those ones where you really know you're going to be using it, and so it makes sense to take advantage of that. Then we have on demand, as I mentioned, and finally spot, which is our unused capacity, which again offers significant discount over on demand, but has the risk that that is unused capacity, and therefore if somebody needs to use that capacity that's an on-demand customer, then those spot sessions will be terminated. So what we typically find is that a combination of the 3 gives the best cost of optimization, and we'll happily help you to navigate through that and give you our best suggestions to get the best cost. Now, of course, we couldn't do this all alone, and we have a really extensive partner network, and particularly for HPC and CFD, this is pretty much all the application partners, all the ISVs. We also have a strong connection with many of the open source codes, technology partners, and consulting partners. And all these companies here and many more that are listed on the website can help your journey to using AWS and take advantage of the cloud for your CFD processes. And I suppose I just want to assure you that even though I've just focused on a couple of codes today, really I can't think of one CFD code that doesn't run on AWS. And if it hasn't run, then I'll happily help you to try it. So really, I would have the confidence that it's any CFD or CAE code, you can get it to run. It's a model that you will bring your own installation, you will install it, you will bring your own license. But it's very easy to access any license servers that are either built on AWS or if you need to just access one on premise, it's extremely common. We help customers do it every single day. So I'd like to just give you the reassurance that if you see a package here, or I didn't mention it earlier, you can feel reassured that you can run it on AWS. So in summary, I'd like to say that AWS can enable you to optimize that whole CFD workflow and really remove the bottleneck of infrastructure. And I actually genuinely think this is as important as improving a turbulence model to give some better accuracy or something. Bottlenecks of infrastructure can make real differences and can limit you from moving towards improved CFD methods. By removing that infrastructure, I hope we can kind of, help the community to move forward and refocus again on moving to these better methods and not have to worry about not having the infrastructure to run them. So the other thing is, of course, that elasticity means that you can just scale this up and down. And of course, you can test things. So if a new code comes out that has a GPU functionality, you can just spin up a GPU on AWS, try it out just for a few minutes or an hour, and just pay for that time. You don't need to go out and buy one. So it's really good for also experimenting and trying new concepts for CFD. As I said, almost all the CFD codes have been run on AWS, and we've helped individuals to full enterprise for hundreds of engineers, tens of applications. So please do reach out to us to talk further. The final slide in this presentation actually has a list of contacts, so feel free to speak to me or any of my colleagues. And with that, thank you very much.